Now, this example, 1 kilogram of air is taken through a Carnot cycle. The initial pressure and temperature of the air is to be, the initial pressure and temperature is to be 1.73 megapascal, that is the initial pressure, and the initial temperature 300 degrees C. Now they have said the initial pressure and temperature. So this 1.73 megapascal should be the pressure P1, and this should be the temperature T1. Now, from the initial conditions, the air is expanded isothermally, okay, to 3 times its initial volume, and further expanded adiabatically to 6 times its initial volume. Now, isothermal compression followed by adiabatic compression completes the cycle. So they start with isothermal expansion. Okay, they start with isothermal expansion, then isentropic expansion, then followed by isothermal compression, and then adiabatic compression. Now, for Carnot cycle, remember, now the first thing is you have to draw the TS and the PV. TS, so this should be the temperature. So the higher temperature, 300 plus 273. The lower temperature is unknown yet. So these are the two isentropic lines. Okay. So which should be your point 1? Yeah. Okay, so this should be your point 1, point 2, point 3, point 4. Okay, so isothermal expansion, isentropic expansion, then followed by isothermal compression, then isentropic compression, back to point 1. So the initial pressure and initial temperature should be based on this. So in this case here, based on what the question has said, this has to be the point 1. This has to be the point 1. Okay, so you have to read the questions now. You have to understand what the question says. Okay, so that is your point 1. So this is on TS diagram. Then on PV diagram, so both of these are the isothermal lines, and both of these is to be the isentropic lines. So your point 1 now, isothermal expansion. So isothermal expansion should be here. So this should be your point 1, point 2, 3, and 4. Okay, and the pressure at this point is 17.3 bar. Okay, so we have 1 to 2, 3, 4, back to 1. Okay, so you have both the PV and TS diagram drawn. So this is the table that we need. Okay, so in this question here, 1 kilogram. So the mass is given. Okay, so that is why this one have to be meter cube. And this one I'm using meter cube. Okay, I'm using meter cube. Okay, because the mass is given 1 kilogram, or it's up to you because it's 1. So you can consider meter cube per kg or meter cube per kg here. Okay, so given is 1. So you have the option of considering as meter cube or meter cube per kg when it is 1 kilogram. 1. Okay, so your point 1, 2, 3, 4, you know the temperature here, that is your T1 and T2. So both the temperatures 573. The pressure here we know 17.3. So we refer to state point 1, 2 to find the pressure P2. Okay, this is temperature. 1 to 2 is isothermal. 1 to 2 is isothermal, right? 1 to 2 is isothermal. So you cannot use the formula. Okay, so 1 to 2 or point 1 itself, point 1 itself, okay, point 1 itself, you can find out the V1. Okay, so once you have found V1, so write into the table. Okay, so then you have state point 2. Volume at state point 2 is 3 times its initial volume that is given in the question. Volume at point 2 is 3 times its initial volume. That means 3 times V1. Okay, V2 is 3 times of V1. So you can find out V2. That is given in the question, and this one. This is given in the question. So you got your point B. Then based on ideal gas law, we can find out pressure P2. Okay, so P2 is the subject. So pressure 5.76. So you can write here 5.76. Okay. Then state point 3. That means this point here. Okay, they say the volume here is 6 times the initial volume given in the question. Volume at state point 3 is 6 times the initial volume. Means the volume here is 6 times of this value. This statement is given in the question, yeah, remember. So you have got your V3. So put your V3 here. Okay, so remember 2 to 3 is an isentropic process. State point 2 to 3 is an isentropic expansion process. So you can look at the diagram. Okay, on. Yeah, I should move it over. So 2 to 3, you can see this is isentropic. Okay, isentropic. Okay, 1 to 2 is isothermal, this case. Okay, so for isentropic, then you can refer to this. Now, this time we are taking pressure to volume relationship. We are not taking pressure and temperature. We are taking pressure and volume relationship. So it's power of gamma. Okay, power of gamma. If you take temperature to pressure, is power of gamma minus 1 over gamma. If you are taking temperature to volume, so power gamma minus 1. Now you are taking pressure to volume, so that is power gamma. So you must know all the 3 formulas, okay, by heart, okay, for all the for isentropic process, for all the relationship between pressure, volume, and temperature. Okay, isentropic process. So for here, for this part, we have to find P3. P3 is the subject. Okay, so we can find out P3. So once you found P3, write it into the table. So that is P3. Then you can consider state point 3 itself using your ideal gas law. Okay, so T3 has to be the subject. This is PV over R. Okay, this is this. Ideal gas law, remember the ideal gas law. And then changing T3 to be the subject. So you got T3, 433K. So you can write 433, 433. Both of these will be 433. Okay, both of these will be 433 because isothermal, 3 to 4 is isothermal. Then you consider 4 and 1 is isentropic compression. Okay, so you can consider for isentropic again. Now pressure and temperature here. Now this something wrong here. This should be power of gamma over gamma minus 1. We are taking pressure to temperature. But then if you are taking temperature to pressure, sorry, temperature to pressure, then is power gamma minus 1 over gamma. Pressure to temperature should be gamma over gamma minus 1. Please double check these isentropic formulas. Okay, this part here is something wrong already. Okay, please double check what you have done in your thermal 1, or you can refer to my second podcast. Okay, I've given you all these formulas for isentropic process. So what you can do from here, you can find out pressure P4. But remember, this is something wrong here already. Okay, temperature to pressure. Okay, so pressure to temperature, this should be power of gamma over gamma minus 1. So you can find out your P4, 6.5 bar. Okay, there's something wrong here already. Please double check your work later on. State point 4, then you can use ideal gas law to find out this empty space here, for this empty space. So once you got your V4, then write it down. Okay, so you fill up the whole table. So once you fill up the whole table, you can find the network, you can find the work ratio, and so on. And once you have got these tables here, redraw your PV or TS diagram accurately. Now we need to make use of the PV diagram later on. Something wrong. This diagram, something wrong already. Please double check the whole thing, yeah? Hope you all can hear what I say. Okay, so this is for the change of entropy formula. Remember, that is during an isothermal process. Okay, during an isothermal process. So once you have found out the change of entropy, okay, now we can make use of this to find out the network and the heat supply. Okay, so once you got this network and heat supply, you can find out the thermal efficiency for Carnot cycle or the Carnot efficiency. Okay, so this is the thermal efficiency or the Carnot efficiency. And you can find out the gross work expansion, work 1 to 2, that means work 1 to 2 is isothermal. Work 1 to 2 should be equals to heat 1 to 2 because it's isothermal. During isothermal process, remember, change of internal energy will be 0. So therefore, work is equals to heat. So you can consider work to be equals to the heat here, 1 to 2. Okay, 2 to 3. So work done 2 to 3. You can consider this. Remember, there are a lot of formulas that you have done, you have used in thermal 1. So you have to apply in your thermal 2. Okay, so okay, that is work 2 to 3. So this will give you the gross work expansion. Okay, and from there you can find out your work ratio with your network and gross work expansion. Okay, now if let's say the question wants us to find the mean of mean effective pressure. Now this I've explained during the last class. Okay, mean effective pressure is defined as network over length of PV diagram. So we have got our network, the length of PV diagram. Now this is your PV diagram. So the length should be referring to the distance between the two outermost points. So this length here, okay? So that should be 0.56 minus 0.096 for the length of PV diagram. So you've got your MEP, that is mean effective pressure, to be 93.1 kilonewton per meter square. Now what I want you to do is, please redo these two questions on your own. Please redo and find out my mistakes. That is what I want you to do. Okay? That's for Carnot cycle, examples for Carnot cycles. There are few more examples which I will attach into your blackboard. Okay? Thank you. Thank you very much.